are raised to represent that quantity. An expression for a physical quantity in terms of its base quantities is called the dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. We will now learn about the uses of these dimensional formulae and dimensional equations. We know that a dimensional equation is the equation among the dimensions of a quantity and not among the magnitudes. Thus, when we write L plus L, as shown, we mean length added to length. So we get length again. It is not 2 times L, as we are not adding the magnitudes of the length. This property of a dimensional equation can be used to check the dimensional consistency of equations by analyzing the dimensional formula of quantities on both sides of the equation. For example, consider the motion of a body moving with an initial velocity u and uniform acceleration a, having made a displacement s in a time interval t. The motion of the body can be represented by the equation s is equal to ut plus half at square. Let us now verify the consistency of this equation using dimensional analysis. On the left-hand side of the equation, we have displacement s. This is basically length and its dimensional formula is L. On the right-hand side of the equation, we have 2 terms, each involving the product of 2 different quantities. The first is ut and the second is half at square. When the magnitudes of 2 or more physical quantities are multiplied, their dimensions are also treated in the same manner as done with ordinary algebraic symbols. In this case, in the first term, it is the product of velocity and time. The product of the dimensions of these quantities is Lt power minus 1 into t, as shown. On simplification, we get L. The second term on the right-hand side of the equation is half at square. Half is a constant and thus does not have any dimensions. In the first term, it is the product of acceleration and time square. The dimensions of A are Lt power minus 2 and that of t are t. Thus, the dimensions of at square are as shown. Taking the dimensional formula of the physical quantities in both the terms on the right-hand side of the equation, substituting their corresponding dimensions and simplifying, we find it is equal to L, which is the dimension of length as obtained on the left-hand side of the equation. Thus, the dimensions of the quantities on both sides of a given equation are the same. This proves that the equation is correct. It is very important to note that physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. This principle is called the principle of homogeneity of dimensions and is useful in checking the accuracy of an equation. This principle can also be used to derive expressions for physical quantities if the other quantities on which it depends are mentioned. For example, we can derive an expression for the time period of a simple pendulum, assuming that its time period t depends on the length, mass of the pendulum, and the acceleration due to gravity at a given place. Let us take the constant of proportionality k as 2 pi. We assume that the time period is proportional to L power A, M power B and G power C, where A, B and C are constants. Replacing the proportionality symbol, we get a constant k. Hence, the time period is equal to k into L power A, M power B, G power C. We now need to find the values of A and B using dimensions of the physical quantities on both sides of the equation. The dimensional formula for time is T. The dimensional formula for length is L. The dimensional formula for mass is m. The dimensional formula for acceleration due to gravity is Lt power minus 2. The constant does not have any dimensions. Hence, the dimensional formula of the quantities on the right side of the equation is simplified as shown. Let this be equation 1. The dimensional formula of the quantity on the left side of the equation is as shown. As we do not have the term for m and l on the left-hand side of the equation, we take their powers to be 0 as shown. Let this be equation 2. Equating equations 1 and 2. We compare the powers of the base quantities on both sides of the equation. Thus, we get b equal to 0, a plus c equal to 0 and minus 2c equal to 1. On simplification, we get the values of b equal to 0, c equal to minus half and a equal to plus half. Thus, the expression for the time period of the simple pendulum becomes 2 pi into the square root of L by G as shown. The value of k, which is equal to 2 pi, cannot be found by using dimensional analysis. However, this method cannot be applied to derive equations where addition or subtraction of different terms is involved. For example, we cannot derive the equation S is equal to ut plus half at square using dimensional analysis, even though we checked its dimensional consistency. Dimensional equations can be used to convert units of a given physical quantity from one system to another, and to thus find the conversion factor. For example, consider the physical quantity force. The dimensional formula of force is mLt power minus 2. The SI system of unit of force is Newton, and its CGS unit is dyne. Hence, 1 Newton is equal to 1 kilogram into 1 meter into 1 second power minus 2. Similarly, 1 dyne is equal to 1 gram into 1 centimeter into 1 second power minus 2. Now, we divide 1 Newton by 1 dyne and then find the ratio of Newton to dyne as shown. Thus, 10 power 5 is the conversion factor to convert Newton to dyne. Dimensions are generally used as a basic test to check the consistency of an equation, where there is a doubt regarding its correctness. However, this test cannot be completely relied upon, especially in the case of dimensionless quantities or functions. Dimensionless constants cannot be obtained by this method. For example, the arguments of some dimensionless functions such as trigonometric, logarithmic, and exponential functions cannot be obtained using dimensional analysis. The ratio of similar quantities results in a pure number, which is again dimensionless. For example, angle is the ratio of arc length to radius, which is length divided by length. Absolute refractive index of a medium is the ratio of the speed of light in a vacuum to that in a given medium, which is the ratio of speed to speed. The test of consistency of dimensions not only tells us the consistency of units, but also helps the user ignore the units to be mentioned and conversions among multiples and submultiples of units. If an equation is put to the consistency test using dimensional analysis, and if the equation fails, it means that the equation is proved incorrect. If the equation passes the consistency test, it does not mean that the equation is correct. Thus, an equation proved to be dimensionally correct need not be an exact equation, but an equation that is proved to be wrong dimensionally must be a wrong equation. The dimensional analysis method is very useful in drawing relationships between various interdependent physical quantities. This analysis can only test dimensional validity, but not the exact relationship between the physical quantities in any given equation. The dimensional method cannot differentiate between physical quantities which have the same dimensions. For example, even though the quantities energy and torque have the same dimensions, they are completely different in every sense.